So I'm not going to say, instead of is probably too strong a phrase. I should have used in addition to or supplementing, because many high-tech methods, of course, are invaluable. We have to use the math programs. We have to use the stat programs. We use email, plotting, and graphics, and programs to make reference lists for us, and LaTeX to make our equations look good. And those are all fine for their purposes, but they're only appropriate at certain times. So they have to simplify our lives, and they have to be consistent with psychological principles of effective teaching and communication. And I'm going to show you where sometimes they're not, and why I say that. I'll tell you some of the principles behind it. So here I would like you to think in terms of the following. If you had the following technological advance, would you like it? It's a McWilliams 2 word processor. I've highlighted some of the features that I think would be great for us. It's portable, it's very small and light, it prints characters in every known language. Graphics are fully supported. You can write equations of any kind of complexity, size, infinitely variable margins, type sizes. You can do anything with this wonderful technological advance, which is pictured here. So this is the McWilliams 2. You use 2 because, of course, it's a number 2 pencil. But the idea here is, ask yourself when you're doing things, if you're writing an equation or you're drawing a picture or something like that, which do you naturally do? Do you do that on the computer? Do you naturally pick up a computer and start writing equations in LaTeX? Most people no. Most people do what I do, is pick up a pencil. But we think we should do everything on the computer. We think we should do everything high-tech, because technology shapes our behavior. Edward Tufte pointed this out for PowerPoint. He has a little chapter in one of his books on the cognitive style of PowerPoint. And in case you don't know already, he doesn't like it at all, because it tends to encourage people to do just what I've done here. This is a bulleted page. And Tufte says PowerPoint encourages everybody to do this because it automatically, by default, puts a bulleted page for you to fill in. And so you tend to fill in bulleted page after bulleted page, and he doesn't like it. So he says, just because you can do something that's high-tech doesn't mean you should do it. And I like the low-tech way for a lot of reasons, both for me and for my students, because for the students, writing things down and drawing things themselves forces attention to details that they would otherwise gloss over. And the additional benefit for me is usually it's much quicker to write something down. And the other thing is it slows you down when you're doing it. You don't just present a slide that's already made up, so you're not rushing through the equations. Look at this equation, look at that equation, look at this. No, you can't do it that fast. People get lost when you do it that way. As an example, I did an equation 2 different ways. I said it in tech, and I wrote it by hand. One took me about a minute, one took me about 10 seconds. And my handwriting isn't too terrible, so it's not too bad. Tufte isn't the only one who agrees that high-tech isn't always preferable. Dilbert also does. I don't know if everybody can read this from where they are, but Dilbert's boss says, your PowerPoint slides impress the executives so much that they're changing our entire strategy. And Dilbert says, but those slides were nothing but a bunch of garbage dressed up to look good. And the boss says, that's what our new product line will be too. So you can make something look fancy. It doesn't mean the content is good. So how do we apply cognitive science and educational psychology rules to teaching? That's what they should be good for. I'll just go over these kind of quickly. I can't go into them in a lot of detail, but really a lot of what I mean is summarized in the old joke, because I'm teaching in New York City, so I always ask the students this. I say, when the tourist goes up to the traffic cop and says, how do you get to Carnegie Hall? What's the answer? Practice, 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 right? So that's how you get to Carnegie Hall, and I say that's how you succeed in statistics. You practice, practice, practice. And if you don't like the simple, joking way of discussing it, you can always tell them to go read Anders Ericsson's either article or his long book or something about the same thing. It's 800 pages saying practice, 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 with a little bit of what makes good practice. There's more to it than just practice, because if you practice the wrong thing thousands of times, you don't get very far. But so there's a little more to it than that, but it really is a lot of that. So how can we help students practice, practice, practice when they're used to just receptive learning? And you normally think of lectures that way, right? Lecture is receptive learning. I try to turn it into something different in a way I'll tell you about in a minute. So I want them to be doing things while I'm lecturing. I want them to be thinking, writing, maybe programming in some cases, and not just doing data analyses, but writing equations, writing mini results sections, drawing diagrams, and so on. So, and another psychological principle that influenced me in my style of teaching is George Miller's magical number 7. Which reminds me that learners can only deal with a few concepts at a time, a few new ones, that is. Eventually, they can combine those discrete things into larger units called chunks and can deal with larger amounts and packages. But at one time, they can only deal with a few things. So a professor of mine back at Iowa State, Lloyd Avant, used to tell me, tell our class, now I'm going to lie to you a little, meaning he wasn't going to tell us all the details, he wasn't going to tell us everything about it, he was going to oversimplify somewhat, but he wanted to make sure we understood the basic ideas, and then we could learn the other things. Another problem I have is that a lot of things are difficult to automate and are slow to construct. So I don't want to spend my time doing a fancy thing. You know, I'm wasting my time. A mathematician, a friend of mine once told me that word processing for mathematics cut mathematical production down by at least 10%, because mathematicians were spending all their time trying to write the equations rather than thinking about the equations and deriving things. So what I do is kind of like the old-fashioned chalk talk. You build up things one layer at a time. You don't put the whole thing on and have them try to figure out what a complicated diagram means. You do it a little bit at a time to add elements and avoid confusion. And equations, as mentioned before, it's the same principle. So I kind of mix the low and medium tech in doing this. I develop the ideas, I ask Socratic questions, I draw pictures, graphs, and equations, but I add a little bit of tech to it in that I have a device at our university which you can put a piece of paper down on it and write on it, and it'll be projected onto the screen. So that makes it nice. And you may remember the old projectors, you had to have the transparencies and all that. It's all different. I can put a book down and show them a problem in the textbook. I can put a piece of paper down and write and display it. So I'm not a total Luddite. I will adopt technology to some degree. And then I can, if I draw something, I can always scan it in and make it available to them later. So I'm going to go through 3 examples, if I have the time to do it, about kinds of things that I'll teach in class. And in class, I might just draw these out. I can't do that here, so I've given it to you sort of in one slide after another to show the progression. And also, it's going to be like going on fast forward, because what takes me anywhere from 10 minutes to a half hour to do to a classroom of people who don't know what I'm talking about is a little different than talking to you. You already know the content of what I'm going to be saying, so it's just to show you how I would do it, so I'll go a lot faster. I give people a display of dots, and I say, there are 2 variables, they're related. It looks like it's what you would call a positive relationship, because people with low values of x have low values of y, high values of x have high values of y. And how do we measure that? That's the concept. I say, how would we measure the strength of that relationship numerically? So I say, well, the fact that we're talking about low values of x and y and high values of x and y means we're thinking of a dividing line somewhere between low and high. So we'll put some lines down there. Where should we put the lines? And of course, they'll come up with the idea of the means. The mean of x, the mean of y is a good dividing point for low and high. Okay, so we have a point somewhere on this. And I talk about, well, if you know that point is above the mean on x, then x minus x bar is positive. And if it's above the mean on y, y minus y bar is positive. And I talk about what happens in the other quadrants, that they're changing from positive to negative. So I say, what about the following idea? I multiply these two, the two deviation scores, x minus x bar, y minus y bar. What will that be in all the different quadrants? Think about that. So they look at points in each of the different quadrants, and they come up with the fact that it's going to be positive in the positive product in the upper right-hand corner, a positive product in the lower left-hand corner, negative in the other two quarters. And I say, so what does that mean? You look at these data. If I were to add up all the products of the deviation scores for all these points, what would happen in this case? And they can say, well, there's a lot more positives than negatives, so it'll add up to a positive number. I say, yeah, okay, so let's go on. What about the other cases? So it's positive in this case. You look in the lower left-hand corner, that looks like something that you'd want to say there's no relationship. So what do you do there? You add those up. What does that look like? Looks like it adds up to about 0, right? And in the bottom right-hand part, I say there's a lot of points in the negative quadrants. What do you think will happen? Okay, so I say that's fine. So now we got a measure of a numerical measure of the strength of the relationship between two variables. We're all done, right? We go home, and I say, wait a minute, class, wait. What if you had 10 times as many points, but they were in exactly the same place? What would happen? And they say, oh, okay, so it'd be 10 times as big. I say, do you want that to me? It's a 10 times stronger relationship? No, oh, maybe we ought to do something about that. So I say, no, we better divide by n, but I'm going to lie to you a little. I'll divide by n minus 1. I won't tell you exactly why, but we'll skip that for now. So I'll say, we'll talk about the average. So that's called the covariance. And I say, well, that's fine, but what happens if you got different scales of measurement and you change the scale of measurement? What happens? And you say, oh, my golly, I don't know. So I say, what about if you divide by the standard deviation of x and the standard deviation of y? You got z-scores for x and z-scores for y. Now you got the average product of the z-scores of x and y. That's called a correlation. So that's how I developed that concept. Yeah, it takes a long time, for a new student to see that, but they understand what's going on conceptually when I do that. Let me go to the next example. Teaching people HLM. It's just regression, right? HLM is just regression. So I say, suppose you got a teacher. The teacher's in a high school. Teacher's looking at the relationship between two variables. They plot a regression line. Looks fine. You know how to do the regression line. Everything's okay. Now what I tell you is I've got a whole bunch of teachers in a whole bunch of different schools. Each one does a study. They each get a regression line. They each have an intercept, each have a slope. I don't bother with the residuals for a while. I just tell them, start with intercepts and slope, lie to them a little. And then I say, okay, there may be, the different schools may have different intercepts. They may have different slopes. We can test maybe whether they have more than you would find by chance. If so, how do you explain that variation? And then I say, well, suppose we have the proportion of students in the academic track in each school. And I look at that, now we got another data set. The data set's not a data set of individuals, but a data set of schools. I want to see what explains the variation in the intercept and the slope, so I do more regressions. But now it's a regression of different data set, that level 2 data set, and we get new parameters describing that. And again, I don't talk about the residuals at first, but put them in later. So that's the kind of thing I would build up, just little by little. I can draw it as I go along, and they'll draw it, and they'll have to reproduce what I do and remember what it looks like. Third example, I talk about vectors and matrices, and they're very confused, of course, about vectors and matrices. So I use this example. I say, suppose you start at the origin, that heavy dot in the bottom left-hand corner, and you want to go home, as evidenced by that arrow pointing towards Y. That's your home. And you can't go straight home because it's a long ways. But you can go on the railroad. The railroad's going in the direction X. It's not going straight toward your home. It's going in a slightly different direction. And I can vary the angle and show them what would happen with different angles. I say, you can go any place on that railroad. The railroad will stop anywhere. Where do you want it to stop? Well, you want it to stop where it's the shortest distance to your home, right? So you stop someplace and say, I'm going to get off and walk the rest of the way home. And how do you decide where to stop? How do you make E as the error or the residual? The residual's the remaining distance for you to walk. How do you do that? And I say the best thing is when you're at right angles to X, when you're orthogonal to X. Why is that? All right, they think about it a while, and I say, suppose you picked a different place to get off. And you had to walk the distance h. How do you know whether h is longer or shorter than e? And they say, oh my golly, it's a right triangle there. H must be longer than e because h is the hypotenuse of the triangle. That must be longer. Therefore, the shortest distance is e, and that makes a right triangle there. And then I talk about how the sum of the Pythagorean theorem says the square of the hypotenuse of the big triangle, which is the length of y squared, is equal to the length of the predicted y squared plus the length of the error squared, and show them how things work out pretty well using the Pythagorean theorem. Now I'm lying to them a lot there. I'm not showing them about centering. I'm not showing them about what X is in multiple dimensions and things like that. But it gives them a good basic conceptual idea of what's going on. And as I draw it, they draw it, and they can follow what's going on. So in conclusion, I think that low-tech and middle-level tech methods are still useful for teaching statistics. They're very flexible. They're very fast to use. They allow the students to do things and follow you along actively so that they're not just sitting there passively. They can think about these things as they do them. The high-tech methods are often used to implement these things, but they don't improve upon them. They're just prettier. They're just prettier. They don't add information at all. And I want to give finally credit for the term appropriate technology, which I adapted and modified here. This is Fritz Schumacher, who authored the book Small is Beautiful, about some of these ideas in economics and in developing countries, which I appropriated for use in statistics. Thank you.
Any questions?
And the answers. That is true. If you have horrible writing or you can't draw a straight line, you're in trouble. It's bad.
Line's not a problem. It's writing.
Writing? Yeah, okay. If you can't write, you're in trouble. You're in trouble. I suggest calligraphy as an exercise.
Better go with a different profession, though.